So this session, title is A Scalable Ensemble Approach for Building and Visualizing Deep Code Sharing Networks Over Millions of Malicious Binaries. And Josh Saxe is going to talk while I turn the lights down so you can see his cool slides.
Okay. How does this volume level? All right. Okay. Okay, so I'm Josh Saxe. I'm Principal Research Engineer and Associate Research Director at Invincia Labs. I'll just start with a little bit of just introduce my group and myself. So the group that I lead at Invincia is the data science group. We our disciplinary areas are machine learning, natural language processing, and information retrieval, and data visualization. And so we have people who are experts in those three fields, and we work on applying those disciplines to cyber security problems. So you'll be seeing sort of a slice of our work today. I don't know if anybody here was at my talk last year. You saw sort of another piece that I'll touch on a little bit during the talk today. My background, I grew up as a teenager in the security scene, actually as a malware author, and it turned out to be a decent career choice, although I didn't realize it at the time. So now I'm working on malware analysis and AI and visualization techniques. Okay, I'm going to go quickly just because it's a short talk. So start with an obligatory motivation. So there have been a huge number of malicious binaries observed since the dawn of the internet in the 80s, right? So this is the chart that I'd like to use as a motivation for these kinds of talks. This is from avtest.org. It's a nonprofit that does testing of AV engines, and so they keep track of how many unique malicious binaries have been observed on the internet by the security community. And so if you look at this chart, right, you see it starts in the 80s, 1984, and it's showing cumulatively the number of unique known malicious files that have been observed by the security community, right? So we see this kind of exponential or at least nonlinear growth, right? So very small number of Trojans and viruses and this kind of thing for the first couple decades of the internet, and then you see this explosion starting really in the last decade, right? And so the vast majority of the malware that's out there has been produced in the last 7 years or so, right? And we're up to about 200 million malicious binaries. So there's a lot of malicious stuff out there, a lot of unique malicious files, right? But we'd be naive to think that they were all unique, right? These files are actually oftentimes variants of one another. They're, somebody's taken a given IRC bot and modified it slightly, right? Or they're using a polymorphic generator to randomize parts of the binary so that they compile down to different hashes, right? To evade the most elementary kind of malware detection. So we've done a lot of research around identifying similarity relationships, right? Trying to reduce down this massive data set that we can actually analyze it in a more efficient manner. So I'm just going to give some background on some of the research that we've done in my group. This visualization is sort of a sum up of some data mining and visualization work we did on comparing dynamic traces of malware samples. So what we did for this experiment was ran a bunch of malware samples, actually thousands of malware samples in a sandbox that we created in our lab. This is just a small subset of them. Each one of these rows represents a malware sample. So it might be hard to see, but this text label says menti.gnsi. So that's an antivirus label for an individual malware variant, right? And then on the right you see this color-coded sort of this color-coded band represents the different discrete behaviors the malware did in the sandbox, right? So I haven't broken it out into actually categories of behaviors, but like this tan, sort of bar here might be the malware downloading a file, right? This might be installing a Windows service, right? And what you see down vertically, right, are these bands of color, which represent identical behaviors, right, that these malware samples have done. So we see there's a big sort of cluster here, right? Whenever you see a rainbow, that's some variation in the malware's behavior. So there's this cluster structure, right, in malware's dynamic runs. And usually as malware analysts, right, we analyze one sample at a time, but it helps to see the forest for the trees, right? So that we can reuse analysis and this kind of thing. We've also done similar experiments on static features of malware. So here each one of these bars, again, is an individual malware sample. In this case, we looked at a family of IRC bots, K-bot samples, and now we're looking at subroutines that we pulled out of the static executable. So basically, little subgraphs of the control flow graph, right, that represent procedures. We've color-coded them based on a sort of fuzzy hash that we've done on them, and then we've done matching. And so these sort of rainbow streaks through this malware represent similarities, right? Genetic similarities between the malware samples. But we also see some variation, right? And then finally, we've also done, sort of in recent work, we've been looking at malware images. So we actually pull out the visible images from malware binaries, so desktop icons, button skins, that kind of thing. And then we're using computer vision techniques to actually find near duplicate images or images that appear similar to the human eye. In this visualization, we're seeing each one of these boxes, right, is an individual malware sample. The links between the boxes show that our computer vision algorithm identified visual similarity, right? And so we see this cluster of pizza malware, right? Or these malware samples that have desktop icons as pizza slices. I'm not sure quite why, but you can see there's reuse of even graphical assets within malware. So there's all this sort of genetic and phenotypic similarity in these large malware data sets that we could take advantage of to get a sort of large-scale demographic view of the world of malware. So that's great from a scientific perspective, and it's sort of interesting, right? But why should we actually care that there are these similarity relationships? So there's a bunch of, I think, strong motivations for doing research in this area. One is just identifying reused code. So code plagiarism between malware samples allows us to reuse analysis work, right? As white hats. If I'm a biologist and I've done a lot of work on horses, and then all of a sudden I discover that zebras exist, right? So I don't have to start from scratch, right? I can take advantage of the genetic similarities between the two species, and the same goes for malware, right? It's much better not to have to start from scratch, and usually probably we don't, right? Because we've often analyzed variants of malware that there's new malware coming out, but oftentimes it shares code with older malware. Another thing is, for doing attribution, right? Understanding, so if you know one malware sample was created by an actor that you're tracking, another malware sample that you observe, it was quite possibly generated by that same adversary, right? But we need to be able to infer shared code relationships in order to be able to leverage those clues. A third motivation is in triaging which malware samples actually deserve our time as analysts, right? So is a new malware sample just another instance of the same old crimeware, right? Generated by a non-sophisticated actor, or is it genuinely new? Is it a genuinely new software lineage that we've never seen before, right? That kind of malware might merit more attention. But again, we need to do the code sharing analysis in order to make that decision. And finally, there seems to be sort of a new trend, right, in the security space around how we do detection, getting away from antivirus signatures and moving towards detection methods that take more computational horsepower and leverage sort of big data analytics, right? And so we think doing shared code analysis over millions of binaries is a piece of that new trend, right? So if we can, instead of deploying a few thousand AV signatures to an endpoint, or even tens of thousands of AV signatures to endpoints, if we can upload files to the cloud, right, and compare a new file we've never observed before to tens of millions of malware samples based on its genetic attributes, we think that can be a more robust way of doing detection. So these are all reasons why it's useful to look at malware similarity networks. Just checking the time to make sure I don't run out. Okay, so that all sounds great, but there are these hard technical problems that stand in the way of actually doing similarity analysis over enormous malware corpora on the scale of malware that we see on the internet today. And so the rest of the talk I'm going to be focused on the research that we're doing around how to address what those technical problems are, and the research that we're doing around how to actually address them. So the first sort of major constellation of technical challenges is around the cat and mouse game of malware obfuscation. So probably everybody knows about the categories of techniques that are on this slide, right? So packing, code randomization, anti-debugging, and anti-virtual machine methods. Thin VMs, like if anybody's ever encountered, have been so unfortunate as to encounter the VM Protect packer, right, that actually runs malware on its own custom VM with randomized bytecodes and this kind of thing. These are all obfuscation methods that make code sharing analysis difficult. And then there's the scalability problem, right? So if you think about how we do code sharing analysis over large malware corpora, right? We have to fill out a matrix like what we're seeing on this slide, right? So let's say we have 4 binaries, right? Binary A through binary D. We need to do a comparison between binary A and binary B, right? Binary A and binary C, binary A and binary D, etc., right? So we need to compare all pairs of malware in order to understand the genetic similarities. So it turns out there's an equation that gives us the number of, so there's a simple equation that gives us the number of comparisons we have to make. And it turns out that the problem is quadratic, right? This equation gives us the number of evaluations we have to do where n is the size of our corpus. Just to give you a sense of how intractable that problem, how intractable that makes the problem of malware comparisons over very large malware corpora. If we were to analyze all 220 million malware samples that I referenced from the AV test slide, that would take this number of evaluations of pairs of malware, right? Which is a number that I don't have English words for. So it's really infeasible, right, to actually do all comparison analysis on such large corpora. Okay, so so it's like mission impossible, right? How do we actually pull off dealing with obfuscation, which, like methods for comparing malware that get around those obfuscation strategies tend to be computationally intensive, right? But then we have this other problem, right, that we need to scale our analysis to deal with lots and lots of malware, right? So it's a really interesting and fun and hard problem to figure out how to do this. So the sort of nuts and bolts of what we have to do, right, is design a mathematical model which allows us to infer malware code sharing, right? We can't directly observe the source code in the malware author's IDE, right, and compare it that way, right? We get, that's actually not observable, right? So we need to use these other sort of proxy signals, right, like n-grams of instructions or printable strings or dynamic traces, right? So, but we need some way of modeling malware similarity mathematically. And then we have to scale to millions of samples and figure out a way to do that, and that's resilient obfuscation techniques. Okay, so just to give you sort of an intro to how people in the research community have approached this problem, right? Usually malware samples are modeled in a very simple way as sets of features, right? So pull out all the API calls a malware sample makes when we run it in a sandbox, or pull out all the printable strings from the malware sample, or all the PE header attributes, right? And then create a Venn diagram between any two malware samples and compare and look at the size of the overlap between their features, right? And the math down here, right, for Jacquard index gives you sort of an equation that allows you to compute a principled and normalized set distance between any two malware samples represented where their features are represented as sets. So here's what the results look like when we compute that kind of simple similarity model on a corpus of malware. Here we took about 2,000 malware samples from 7 different malware families. So the names of the families are here along the rows: Depato, Pasta, Score, VBNA, Web Prefix, Xtuber. These are Kaspersky antivirus labels. Thank you. And then so what you're seeing. So also let me just introduce how to read this matrix, right? So basically what we want is squares that look like this, right? So each pixel in this matrix represents an individual similarity computation. So like the pixels here are showing us comparisons between web prefix samples, right? And the fact that these pixels are white means that we've identified positive similarity between malware samples that are all part of this web prefix family, right? So this is a very pleasurable result for us as malware researchers, right? To see this big white block, it means that our simple model is actually detecting quite well, right, these genetic similarities between malware samples. This is unfortunate, right? That what happened with VBNA. This square is very dark, which means that we're getting a lot of false negatives, right? Like our simple model is saying that those malware samples are not similar to each other. These over here, out in this black place, are true negatives, right? We don't want to be identifying similarities between malware samples that are not part of the same family. These are possibly false positives. I'm not sure if you can see these guys very well, but there's a white streak here where we're saying that Score and Pasta are part of the same family, and it's not true, which we know is ground truth. False negatives, and then those are true positives. But we think we can do better than this, right? We think we can fill in all of those squares and make them much more white. So ways of doing that that I'm going to present right now are better feature weighting. So not all shared PE header attributes mean the same, should be granted the same weight in helping us decide that two malware samples are similar, right? Doing better comparisons, right? There might be better mathematical models for comparing malware samples. And then finally, actually scaling things up. So in this first experiment, we haven't really worked on scalability. Okay, so our first innovation, and I don't have very much time, so I'm going to actually rush through this stuff, and people can ask me questions later. First innovation is weighting the feature space. So we have a method for counting trillions of features in malware that uses an approximation technique. Ask me about it later. And we're releasing source code for doing this kind of very, very scalable counting in the conference materials if people are interested. But that's how we weight the feature space, and we get better results that way. So what we're using is called a Morris-Bloom counter, which is actually a really cool thing, which I wish I had time to talk about. But, and then the second approach that we're taking, which is novel, we believe, is instead of using one similarity method, right? Instead of just looking at PE header features or dynamic traces or file homologies, we're taking a bunch of different sort of cameras and honing them on a malware corpus, right? Looking at different things, right? We're looking at instruction engrams, so basically sequences of instructions that we've extracted from malware and how much they overlap between any two malware samples. We're looking at dynamic trace similarity, so we're running the malware samples in sandboxes and looking at how similar those dynamic behaviors are. We're looking at file byte sequences, so any number of things we're looking at. I have 4 on this slide, but we've done experiments using any number of sensors. And so the intuition behind using all of these different sensors is that a malware author who's trying to obfuscate the relationship between the two malware samples can defeat one of these methods pretty easily, right? So if they want to defeat our ability to understand genetic similarity between two of their malware samples based on instruction engrams, right, they can use a packer, right? But if they use a packer, we can run the sample in a sandbox, right, and detect that their unpacker code is actually the same, right, when we run it in the sandbox. And so we have so basically we're thinking about this from a sort of game theoretic perspective, and thinking about how hard can we make, it's possible that it's much harder for a malware author to defeat 4 sensors combined altogether, right, than it is for them to defeat to any one of the sensors, is the basic idea. Okay, and then our third innovation is using a probabilistic approach to doing the similarity comparisons. And so I don't really have time to go into the math, but I'd be happy to talk in detail about it after the talk. But sort of the result of the way in which we're doing the similarity comparisons is that we actually don't ever compute similarity between two malware samples that are not similar. And that's because when we extract the feature from the malware sample, we insert it into a sort of probabilistic database. And this database has this special property, right? So it's way different than the way that you think about databases normally. So instead of writing like a SQL query, you query by example by giving it a numerical malware feature vector. And then the database returns results in a probabilistic way. So this chart sort of shows how that works. Basically on the x-axis we have the similarity of any other sample in the database, and on the y-axis we have the probability that a given sample will be retrieved from the database. And so samples that are not similar to a query sample have a probability of being retrieved that approaches 0. And samples that are very similar to the query malware sample have a very high probability of being retrieved in the result set. And so using this probabilistic index, we can avoid doing the direct computation of similarity on the vast majority of malware samples, and just limit our comparisons to the malware samples that are highly likely to be similar. Okay, so I'm going to go over some results quickly, and that hopefully will sort of demonstrate how this all works. Okay, so I'm going to show results from each one of our similarity analysis techniques, and then show what happens when we combine them all together. So here we ran the same experiment on the 7 malware families, looking for file similarity between the malware samples. So what we're doing is pulling out sequences of bytes in each file and then comparing how many uncommon byte sequences are shared between any 2 malware samples. And so we see that these results aren't very good, right? So this family Depato, it's all black here. We wish it was a big white square like this, right? So such that we were detecting the similarities between the malware samples and the Depato family, but we detect almost nothing, right? And then these other families we don't do very much better at. There's just one family, this web prefix family, which seems to not do much obfuscation, where we do see that similarity. But then when we take instruction similarity, right, so here we've changed to looking at sequences of x86 instructions, all of a sudden this pasta family shows up, right? We see some of the Depato family. So we can see the change here, right? All of a sudden the similarities become visible. And then when we run the samples in the sandbox and look at similarities between the dynamic sequences, we see a lot more similarity, right? But we also see some false positives. So here we can see almost all the families' similarity actually shows up when we do the dynamic sandbox runs. And then finally we look at the PE headers and compare those features. And then finally in the last slide we're actually combining all the metrics together. And so what we find is that by combining all these similarity metrics together, we can do better than any one similarity metric, right? We can weed out false positives and also false negatives, right? Okay, we were formally evaluated on this approach by MIT Lincoln Labs against 4 other competing methods for doing malware similarity at scale, and we evaluated it as the best approach, and we were the only ones, I believe, doing this ensemble similarity approach. So we really attribute the effectiveness of this approach to using all these different methods at once, right, and then integrating them in an intelligent way. Okay, so all this stuff is going to be, so this isn't just a research project. So all this stuff is actually going to get released in the next month on a public web portal, Sinomics.org. This is a screenshot of the Sinomics site. So you can do network analysis of your malware corpora on this site and also compare your malware samples. Thanks. I'm almost out of time, so I'm hurrying. So you can do analysis in your malware corpora on this site. I would give you guys a demo, but don't have time. But Giacomo, who's in the audience and who's a member of my team, is going to be giving a demo at Black Hat Arsenal tomorrow. So if you want to try out this software and get a more in-depth description of how it works and how you can use it, please come by our presentation. But here basically what you're seeing in the screenshot is network analysis over some data sets we uploaded into our system, right? So you can use the system to understand the relationship between a single malware sample and the other malware samples in our database and other malware samples that you've uploaded to our system. I mean, this is available free of use. It's an open tool. We're hoping that people in the security community will start using it so we can integrate people's knowledge and malware data sets together. We also provide a similarity, a sort of in-depth similarity analysis view that gives a feature matrix, right? So here we're seeing comparisons between 5 malware samples that our network analysis tool deemed to be similar. We also provide the crowdsourced capability, detection capability, which I talked about last year, basically a way of using machine learning to profile malware samples capabilities. So these are all rolled into this tool, which you guys can use for free if you're interested in, for malware analysts in the audience. Okay, so that's it. So we're releasing the software on the website. It's on Sinomics.org. We're also in the conference materials releasing a machine learning library for doing highly scalable counting of discrete items over using a very efficient data structure. So you can adjust the size of the data structure depending on how accurate you want the counts to be. But in 64 megs of RAM, you can count trillions of unique items, and we found it very useful in our machine learning work. Okay, so that's it. Please come by our booth. We have a booth on the vendor floor. And again, come by our Arsenal presentation if you're interested in the free version of our software we're releasing online. And I'm happy to take any questions if there is time. Okay.